Okay, now that we have done the regular Cournot simultaneous quantity setting game, and we've done the Stackelberg game, where one firm is a leader and one firm is a follower, and it's a sequential quantity setting game, we're going to look at collusion. And we're going to look at, do firms have an incentive to collude? We're going to learn how to find these collusive equilibriums for quantity, price, and profit. And we're going to look into if collusion is a Nash equilibrium. So let's get right into it. Now, before we start though, it's important to think about this with a little bit of intuition. If there's two firms in a market competing with each other, and they collude and decide to work together, then all of a sudden you have a monopoly situation, because you have one firm that controls the entire market made up of these two firms working together, and you have no competitors, right? And therefore, how we're going to solve for the equilibrium quantities, price, and profits is we're going to use the techniques we did for monopolies, which was setting marginal revenue equal to marginal cost and solving from there. So let's get right into it. Now, if you recall, P of Q was equal to 120 minus Q, right? And we know that our cost for each firm, which was equal to 6, and we can assume that the average cost I is equal to the marginal cost I. I represents the number of each firm, which is equal to 6, right? So therefore, we know our marginal cost is equal to 6, and we have to find our marginal revenue. Now, to find our marginal revenue, let's first find the total revenue, right? We know total revenue is equal to the price of each unit, which is P of Q, times however many units we sell. We know what P of Q is. We have it here. So we're just going to sub it into total revenue. It's going to be equal to 120 minus Q times Q. So therefore, total revenue is going to be equal to 120Q minus Q squared, right? To find marginal revenue, we know this is just the derivative of total revenue, right? It's the derivative of quantity with respect to total revenue, which is going to be equal to 120 minus 2Q, right? So therefore, we're going to set marginal revenue equals to marginal cost to find Q collusion equilibrium, right? So we know 120 minus 2Q is going to be equal to 6. If we do a little bit of rearrangements, we know 120 minus 6 is going to be equal to 2Q. 114 is going to be equal to 2Q. So therefore, Q is going to be equal to 114 divided by 2. So Q collusion is going to be equal to 57. Perfect. And we know that price collusion is going to be equal to 120 minus 57, right? And we get that from the price equation right here. So price collusion is going to be equal to 120 minus 57, which is equal to 63, right? And now we can start to see a little bit of the behaviors of these variables in different scenarios, right? If you recall, in the collusion case, right, in the regular, not the collusion case, sorry, in the Cournot case, we know big Q Cournot was equal to 76, and we know price Cournot was equal to 44, right? And we see that when these two firms collude and act like a monopoly, they lower the quantity and they increase the price, right? And that's showing that monopolistic behavior. Okay. One more step, right? We know that Q1 collusion is going to be equal to Q2 collusion, right? The two firms are working together, and therefore they'll share the amounts of, or they'll split the market output evenly between each other, right? Which is basically Q1 collusion is going to be equal to Q2 collusion, which is going to be equal to 57 over 2, right? Actually, let me just write it like this. Q collusion over 2, which is equal to 57 over 2, which is equal to 28.5, right? Perfect. So Q1 collusion is going to be equal to Q2 collusion. These are lowercase q's, which is equal to big Q collusion over 2, right? It's the market output divided by the number of firms working together, which in our case is 2, which is equal to 57 over 2, which is equal to 28.5, right? So therefore, we have all of our variables, right? We know Q1 collusion is equal to Q2 collusion, which is equal to 28.5. We know big Q collusion is equal to 57, and we know price collusion is going to be equal to 63, right? We also know that because each firm faces the same price and they're working together and they're setting the quantity equal to each other, right? They're both sharing the same amount of quantity, or the same amount of output, I should say. We know profit 1 collusion is going to be equal to profit 2 collusion, which is going to be equal to price minus cost times however many units each firm is producing, which is going to be equal to 63 minus the cost, which was 6, times 28.5, which is equal to times 28.5, 1,624.5, right? Perfect. So we can now conclude that profit 1 collusion, which is equal to profit 2 collusion, which is equal to 1,624.5, is greater than profit 1 Cournot, which is equal to profit 2 Cournot, which is equal to 1,444, right? If the two firms collude, they'll make more money than in the Cournot case. So therefore, yes, there is an incentive to collude, right? Perfect. Now the question that we have to ask is this collusion Nash equilibrium, right? And recall that Nash equilibrium occurs when no player has an incentive to unilaterally deviate, right? It's a stable equilibrium where the two players don't have any incentives to change their behavior, right? No incentives to deviate. So in order to answer the question, is collusion Nash equilibrium, we have to find out if there is an incentive to collude. If there is an incentive to deviate, I should say. And this is how we're going to do it, right? We're going to look at a case where we're going to assume that firm 2 colludes, right? And firm 1 decides to deviate, right? Firm 1 deviates, right? We know that if firm 2 colludes, they're going to set their output to 28.5, right? We just solved this in the monopoly case, right? So we know that Q2 is going to be equal to 28.5, right? To find Q1, right? To find Q1, we have to sub Q2 equal 28.5 into BRF1, right? And the reason for this is firm 2 is going to collude and they're going to make 28.5 units and we're the ones deferring. So we're going to put the 28.5 that firm 2 sets their output equal to into our best response function because we want to make as much money as possible, right? So therefore, Q1, when 1 deviates and 2 colludes, is going to be equal to 114, right, minus Q2 over 2, which is going to be equal to 114 minus 28.5 over 2, which is going to be equal to, let me just calculate this. It's going to be equal to 42.0 0.75, right? And let me make sure this is correct. It is. Perfect, right? Now that we have Q1 and Q2, we can find market output, which is big Q, right? So Q1 deviates to colludes is going to be equal to Q1 plus Q2, which is going to be equal to 42.75 plus 28.5, which is going to be equal to 71.25. One deviates to colludes, one deviates to colludes, right? So therefore we know that the market output given one deviates and two colludes is going to be equal to 71.25. We can then find price, right? We know P of Q is equal to 120 minus Q, which is going to be equal to 120 minus 71.25, which is going to be equal to 48.75, right? So therefore, the price given one deviates and two colludes is going to be equal to 48.75. Okay, we're almost there. Now we have to find profits, right? We know that the two profits are not going to be equal to each other because firm 1 is clearly setting their output way higher than firm 2, right? They're deviating. So we know that profit 1 is going to be equal to the price minus the cost times however many units firm 1 sets, given that they deviate and firm 2 colludes, which is going to be equal to 48.75 minus 6 times Q1, and recall that Q1 is equal to 42.75. So this is going to be equal to 48.75 minus 6 times 42.75. So therefore, profit 1 given firm 1 deviates and firm 2 colludes is going to be equal to 1,827.5625, right? And we know that profit 2, right, given that firm 1 deviates and firm 2 colludes, is going to be equal to 48.75 minus 6 times Q2, which is going to be equal to 48.75 minus 6 times 28.5, right? This is the same quantity in the collusion case because firm 2 still colludes. It's firm 1 that's deviating, right? So this is going to be equal to 42.75 times 28.5, right? I got the 42.75 by subtracting these numbers. This is going to be equal to 1,218.375, right? So we're almost there. We know that profit 1 given firm 1 deviates and firm 2 colludes is going to be equal to 1,827.5625. And we know that profit 2 given that 1 deviates and 2 colludes is going to be equal to 1,218.375, right? If you recall, the profit in the case where both firms work together and collude was equal to 1,624.5, right? We just calculated this over here. Profit 1 collusion is equal to profit 2 collusion, which is equal to 1,624.5. If you can see, the profit of the first firm, the firm that deviates, is greater than the profit of the collusion, right? When firm 1 colludes, which was equal to 1,624.5. And we know that the profit of the firm who colludes, and given that the other firm deviates, is going to be less than the profit in the collusion case, right? And from this, we can see that the firm that deviates, right? Firm that deviates makes more profit than in collusive case, right? And the firm that doesn't deviate, the firm that chooses to collude, makes less profit. And we're going to show this actually in a game matrix, right? So let me draw that out right now. And this will really, and so we know that collusion is not a Nash equilibrium because there will be a firm that has an incentive to deviate because they can make more money, right? So let's show this in a game matrix, right? We have this 4x4 matrix. We'll put firm 1 on the x-axis and we'll put firm 2 on the y-axis, right? We'll put BRF here, and we'll put collude here, right? So the first two boxes that are easy to fill out are the BRF box and the collude box, right? We know that in the Cournot case, the regular Cournot case, right, which was part A of our question, we know that each firm makes $1,444, right? So firm 1 makes $1,444, which is the first number, and firm 2 makes $1,444, right? We know if both firms collude, both firms are going to make $1,624.5, right? So firm 1 is going to make $1,624.5, and firm 2 is going to make $1,624.5. Perfect. Now, what happens if firm 1 decides to play their BRF, which is this line right here, and firm 2 colludes? Well, we kind of just saw that, right? Firm 1 plays their BRF, so they deviate from collusion, but firm 2 decides to still collude. They decide to stick to their word. In this case, we know that firm 1 is going to make $1,827.56, and we know that firm 2 is going to make $1,218.37, right? We just calculated this. And if we flip it, what if firm 2 plays their BRF and firm 1 decides to collude? We're just going to swap these two numbers around, right? Because we know that firm 1, which is our first number, right, they are going to make $1,218.37, and firm 2 is going to make $1,827.56, right? So we just completed our game matrix. Now let's show that collusion is not a Nash equilibrium, right? The way we're going to do this is if firm 1 plays BRF, right? If firm 1 plays their best response function, right, which is these two boxes right here, right? Because firm 1 is on the x-axis, BRF is here. So we know that if firm 1 plays BRF, we're deciding between these two boxes, right? If firm 1 plays BRF, what is firm 2 going to do? Well, firm 2 can either play their BRF and make $1,444, or they can decide to collude, but then they would only make $1,218.37, right? So if firm 1 plays the BRF, best response of firm 2 is to also play BRF, right? Because, let me actually move this a little bit back, because 1,444 is greater than 1,218.37, right? So if firm 1 plays BRF, firm 2 plays BRF, we're going to have our box right here. Now, if firm 1 colludes, right, we know that we're going to be in these two boxes. Firm 2 can either play their BRF and they'll make 1,827, or they can collude as well, but then they'll only make 1,624.5, right? We're looking at the second number in each box. So if firm 1 colludes, right, the best response of firm 2 is to play BRF. And we just showed that, right? We just calculated this. If both firms originally collude, and then one firm decides to deviate and play their BRF, they'll make more money. So if firm 1 colludes, the best response of firm 2 is to play BRF because 1,827.56 is greater than 1,624.5, right? So we'll fill in this box right here. Now, if firm 2 plays BRF, right? This time we're switching to firm 2. We're looking at the y-axis. So firm 2 plays BRF. Firm 1 can either play their BRF and they'll make $1,444, or they can collude, but then they'll only make $1,218, right? So if firm 2 plays BRF, best response of firm 1 is to play BRF because 1,444 is greater than 1,218.37. So we'll fill in the box right here. Finally, if firm 2 colludes, okay, we know that we're looking at these two boxes because firm 2 colludes. So firm 1 can either play their BRF and make $1,827.56, or firm 1 can collude and only make $1,624.5. Well, obviously, firm 1 is going to play their BRF because they make more money. So if firm 2 colludes, best response of firm 1 is to play BRF because 1,827.56 is greater than 1,624.5, right? Firm 2 colludes, firm 1 plays their BRF, and they'll make 1,827.56, which is greater than if firm 1 colludes as well, and they only make 1,624.5. Okay. From this analysis, let me also fill in the box right here. From this analysis, we found that no matter what firm 1 does, firm 2 will always play their best response function. And no matter what firm 2 does, firm 1 will always play their best response function. Therefore, we know that play BRF is the dominant strategy, right? It's going to happen no matter what. Dominant strategy. So therefore, BRF is the Nash equilibrium, right? And the reason it's the Nash equilibrium is because if firm 1 plays their BRF, firm 2 has no incentive to deviate. They're also going to play their BRF, right? And likewise, if firm 2 plays their BRF, firm 1 has no incentive to deviate, right? Because if they do, they're going to make 1,218, which is less. They're also going to play their BRF. So therefore, we know that BRF is the Nash equilibrium. No player has an incentive to unilaterally deviate. And we can say that collusion is not Nash equilibrium, right? Because there is an incentive to deviate. So because there is an incentive to deviate. So this is very interesting, right? We're really looking into game theory now. This kind of relates to the prisoner's dilemma, but we're looking at this Nash equilibrium, which is here and occurs when both players have no incentive to unilaterally deviate. Okay. Now that we've solved the collusion case and we've proved that collusion is not a Nash equilibrium, we're going to start looking at multi-period games, right? Up until this point, we've been solving only one period games. We've been assuming that the game only lasts for one period. But now we're going to look at what happens when the game lasts for multiple periods in a finite setting, or it lasts for unlimited periods, right? We're going to start looking at these cases. And we're going to start by looking at the finite case. What happens if the game occurs for a finite period, right? So we're going to look at question D right now. It says that suppose the two firms know that they will play this game for a fixed number of periods, say 3 years. What would each firm's total profits be at the end of the game? Explain how you arrived at your answer, right? Okay. So we know that in period 3, so when we're doing the finite period games, we want to solve backwards, right? In period 3, we know that both players are going to play their BRF, right? And the way you can kind of visualize this, actually, let me start off with the kind of textbook answer of how to solve this, and then I'll go into kind of the intuition behind it, right? So we know that in period 3, we know the game ends, right? And we know that the Nash equilibrium is the Cournot Nash equilibrium. And all that's just saying is that both firms are going to play their BRF. The Nash equilibrium is going to be $1,444 for each firm. That's all that's saying, right? We know that in period 2, right, each firm knows that the other is going to defect in period 3, right? Both firms know the other will defect in period 3, and therefore both firms are going to play their best response function in period 2, right? They're both going to work non-cooperatively because they know that in the third period, they're not going to work cooperatively either, right? So in period 2, both firms know the other will defect. In period 3, we know that Nash equilibrium is still the Cournot Nash equilibrium, which is where both firms play their BRF, right? Which is right here. And we know that if both firms are going to play their best response in period 2, then they're also going to do the same in period 1, right? And we're going to say, and likewise, in period 1, Nash equilibrium is Cournot Nash. Now, a better way to kind of, conceptualize this and think about this intuitively is suppose I'm firm 1 and you as the viewers are firm 2, right? We know this game's going to end in period 3. In period 3, I'm going to want to defect because I know that if I defect and you stay colluding, I'm going to make more money, right? I'm going to make $1,827.56. You're also thinking the exact same thing. You're thinking that if I collude and you play your BRF, you'll make more money. Or if I play my BRF, you don't want to collude because then you're going to be stuck. You're going to make less profit. So you're also going to want to play your BRF, right? So therefore, in the third period, we're both going to play our BRFs. But we also know this in the second period. This is what it means by backward. We're solving backwards. We know that in the second period, we're both going to defect in the third. And therefore, you're going to want to defect now, right? You're going to want to try and defect ahead of the other person, right? But this thinking goes both ways, right? I'm going to want to defect before you, and you're going to want to defect before me. And therefore, we're both going to defect in period 2, knowing that each of us are going to defect in period 3. But then we solve backwards again. We go to the first period. Okay, now both of us know that we're going to defect in period 2. So we're going to want to try and get ahead, and we're going to want to defect in period 1. So the key piece of intuition, or the key takeaway you need to take for a finite period game, is that in a finite period game, acting non-cooperatively is the dominant strategy and is Nash equilibrium, right? So how do we solve for profit now? We know that profit is going to be equal to the discounted profits for the finite number of periods. And what do I mean by this? Well, in the first period, we both act non-cooperatively. We both make $1,444. So in the first period, we both make $1,444. In the second period, we're both going to defect. We're both still going to make $1,444, but we have to discount it, right? And we're going to discount it by using delta, right? Likewise, in the third period, we're both going to make $1,444. So we're going to have to discount it to the squared value, right? So it's going to be delta squared times 1,444. And this is going to keep going till delta n minus 1 times 1,444. And this is how you solve the profit for a finite period game, right? If this game went to 10 years, your last delta would be 10 minus 1, which would be delta to the power of 9, and so on. Okay, now we're going to move on to the infinite period game, right? Question E. Suppose now that the two firms play this game repeatedly forever. Let each of them use a grim strategy in which they both collude unless one of them defects, in which case they will both defect for the rest of the game. Find the range of values of discount factors for which this strategy is able to sustain collusion between the two firms. Okay, now we know that this game is going to last forever, and each firm is going to collude and work together with each other until one of them defects. In that case, they're both going to not work together forever. They're both going to play their BRF and work independently forever. Now, if either firm is to defect, they're going to defect in the very first period. Why? Well, because $1 today is worth more than $1 tomorrow, and therefore defection is always going to happen in the first period in an infinite period game. So how do we solve this question? First, we have to find the one period benefit of defection, which we're going to denote as B. And we have to find the lifetime period cost of defection, which we're going to label as C, right? For the benefit, we know that if both firms collude, they're both going to make $1,624.5 each. Let's say firm 1 decides to deviate and play their BRF. Instead of making $1,624.5 in the current period, they're now going to make $1,827.56 instead, right? So the one period benefit of defection is going to be equal to $1,827.56 minus 1,624.5, which is going to be equal to, let me just calculate it, which is going to be equal to 203.06. Okay, now what's the lifetime period cost of defection? Well, if both firms collude, they're both going to make $1,624.5, but now that firm 1 has decided to deviate, both firms are going to play their BRF and therefore make $1,444 forever instead of this $1,624.5. Therefore, the lifetime period cost of defection is going to be equal to $1,624.5, which is the case that both of them collude, minus 1,444, right? Because now they're both working independently. And this is going to be equal to 180.5. Perfect. Now, what's important to note about this defection is that this cost of 180.5 occurs not in the current period, but in the second period. Because in the current period, right, the firm that defect is making this benefit. So therefore, the lifetime cost can be written as 180.5 times delta plus 180.5 times delta squared plus 180.5 delta n minus 1, right? And you can replace the 180.5 with C, and that would work as well. So what we have to find is we want to find the discount factor that makes collusion sustainable. Well, what does that mean? That means that the cost of colluding must be greater than the benefit. If the cost of defecting must be greater than the benefit of defecting, right? If the cost of defecting is greater than the benefit of defecting, no firm is going to defect and both of them are going to collude. Well, how do we write that? We know that the benefit, B, must be less than C times delta plus, which is the cost, c times delta squared plus c times delta 3 plus the cost of delta n minus 1, but we know this goes to infinity, right? So we don't really worry about the n minus 1. Well, we can actually factor this out, right? We'll get the benefit must be less than c delta 1 plus delta squared plus so on, right? We can just factor out the cost delta. So we know that the benefit must be less than this function right here. But is there another way we can write this function? And it turns out there is. This function is going to be equal to the cost delta times 1 over 1 minus delta, where delta is the discount factor, right? So this is equal to cost delta over 1 minus delta. Boom. So we have everything set up. We know for collusion to be sustainable, the benefit must be less than the cost times the discount factor, right? Times 1 minus, or divided by 1 minus the discount factor, right? And from here, we can actually isolate for delta, or the discount factor, right? We're going to cross multiply. We're going to get benefit minus benefit delta must be less than cost delta, where delta is the discount factor, right? What we're going to do is we're going to factor out b, right? b1 minus delta is, sorry, let me just make sure. We're not going to factor out b, sorry. We're going to go b must be less than the cost times delta plus the benefit times delta, right? We can then factor out the delta, right? We can, let me move this up here. We can divide both sides by c plus b. And what we'll end up getting is our delta critical, which is our discount factor that makes collusion sustainable versus unsustainable, is going to be equal to benefit over the cost plus the benefit, right? And we just solved this. So we know that if the discount factor is less than the benefit plus the cost, we know that if the discount factor is less than the benefit divided by the cost plus the benefit, we know that collusion is sustainable. So that was a little bit tricky because it was a lot of math. It's kind of hard to grasp, but this formula is going to save you in this question, right? So whenever you see this question, the first step is to find the 1 period benefit of defection, which we did. Find the cost of defection, which we did. And then you know that your delta critical, which is your discount rate critical, is going to be equal to benefit divided by benefit plus cost, which in our case is going to be 203.06 divided by 203.06 plus 180.5. We know that our discount value critical is going to be equal to, let me just calculate this. $0.5294, right? Now, how are we going to use this to solve the question? Well, we know that if the discount value is equal to or greater than 0.5294, we know that collusion is sustainable and that the firms will not want to defect because the cost is too high, right? And that's how we solve the question, right? So those are the steps. You want to first find the 1 period benefit of defection, which is B. right? You want to find the lifetime period cost of defection, which is C, plug it into this formula for your discount value critical, solve, and then you know that if your discount rate is greater than 0.5294, the cost of the lifetime cost of defecting is greater than the 1 period benefit of defecting, and therefore it's not worth it to defect. Both firms will collude, and collusion is sustainable. And this is your final answer, and this is how we solve the infinite period question.